Welcome to the deep dive. If you, like us, are fascinated by this whole new world of local AI development, you definitely know the biggest hurdle right now.
Oh, yeah.
Trying to run those huge large language models, the LLMs, on your own machine at home.
The VRAM demand is it's massive. And that means cost, big cost.
Totally. It's the main gatekeeper, isn't it? Most regular high-end gaming PCs, they just don't have the graphics memory.
Nope, not enough VRAM to load up one of the really big advanced models, so you end up stuck with, expensive cloud services.
Exactly. So that's our mission for this deep dive. We're digging into a guide for a really specific custom PC build, one that tackles this cost problem head on. And they did it by making a really interesting choice, a strategic one. They built a machine that, well, if you look at it traditionally, it seems completely unbalanced.
Yeah, on paper it looks kind of weird.
But for this one specific job, maximum local AI performance, it's actually brilliantly rational.
The whole philosophy was super clear. Concentrate the budget, like laser focus. Pretty much every dollar they could scrape together went into the single most critical part for LLMs.
The GPU memory, VRAM.
You got it. Maximizing the build around the upcoming RTX 5090, specifically aiming for that 32 GB of VRAM. That was the target.
Okay, so we're going to unpack that. This whole idea of strategic sacrifice. Why ignoring the usual performance benchmarks, the gaming stuff, actually lets you build a better purpose-built AI machine.
And then we get into the really cool part.
Yeah, the hidden gem.
This deep technical hack, it's not obvious at all. It involves a tiny little sensor.
Yeah.
And it's all about making sure that monster GPU stays cool and stable, but without needing clunky software eating up your resources.
Okay, let's get into it. So why VRAM? You mentioned it's the gatekeeper for LLMs.
It really is. It's not just like a nice to have.
Yeah.
It is the hard limit. It dictates the size, the complexity of the AI model you can actually run locally.
Okay, wait, break that down a bit more. Why is VRAM so much more critical than, say, just raw CPU speed? I think a lot of people focus on the processor.
Sure. So think of it like this. The whole model, right? Billions of parameters. All of that data has to sit inside the GPU's own fast memory, the VRAM, to run efficiently.
The whole thing.
Ideally, yes. If you're running a huge model, maybe a 70 billion parameter one, and you want a decent context window that's the history the model remembers during a conversation.
Right.
That also has to fit in VRAM. If you run out of space,
Come on.
well, either you just can't run the model at all, or the system tries to shuffle parts of it back and forth to your main system RAM, which is way, way slower.
Ah, okay. So performance just tanks. It grinds to a halt.
Pretty much. So the bottleneck isn't really how fast the GPU can do the math. It's whether you can even load the problem into its fastest memory first.
That makes the 32 gigs on that 5090 the absolute non-negotiable core of the whole build then.
Exactly. If VRAM is your hard limit, then getting the most bang for your buck means, well, cutting back everywhere else you possibly can.
Right. That's where the unbalanced part comes in.
Precisely. And this is where they got clever with the platform choice.
Yeah.
Budget magic, really. They deliberately skipped the newest, most expensive motherboard sockets. And instead, they went with the tried and true last generation, the AM4 platform.
Okay, AM4, still
Pretty
solid.
solid.
Yeah.
And that one decision, it dramatically lowered the cost of the motherboard itself and the RAM that goes with it. Big savings right there.
So if VRAM is the bottleneck, does that mean the CPU choice?
Right.
It matters more for just being efficient, maybe low heat, rather than raw speed.
For this specific task,
Yeah.
largely yes. They picked the Ryzen 7 5700X. Now, it's still a perfectly decent CPU, fast enough to keep the data flowing to the GPU.
Sure.
But the key thing is, it's a lower TDP option, thermal design power.
Meaning less heat.
Exactly. It doesn't dump a ton of heat into the case. And that low heat output, that's actually a really important piece of the puzzle for the whole cooling strategy, which we'll get to.
Okay, interesting. So a good, but not top-tier CPU, sitting on a reliable Asus ROG Strix B550A gaming motherboard. Good board, but yeah, not the absolute latest bleeding edge.
Doesn't need to be. Same logic applied to the system memory and the storage drive.
It's sensible.
Yeah. Solid performance, nothing too flashy or expensive. They used 32 GB of DDR4 3600 MHz RAM. Standard stuff, but fast enough. Plenty of system RAM for coding or handling data, but no need for pricey high-speed DDR5.
Right.
And for storage, a fast MSI Spatium M480 Piro 2TB NVMe drive,
Yeah.
PCIe 4.0, quick load times, which is nice, but again, not breaking the bank. You're building a specialist tool here, not a general-purpose machine aiming for benchmark scores.
So the takeaway for you listening is You really need to think about where your resources need to go. If your main task screams for VRAM, like with LLMs, then chasing that balanced high-end build.
Buying the latest CPU platform just because it's new.
Right. It's actually wasting money that could have gone into more VRAM, or in this case, just making the VRAM you can afford possible in the first place.
The machine's design flows directly from its purpose built.
Which leads us straight into the next big challenge, heat. You mentioned that low TDP CPU was important for the thermal strategy.
Foundational, yeah.
Because once you fire up that RTX 5090 and run LLMs on it constantly, well, you're basically running a small furnace inside your PC case.
Absolutely. That thing under sustained load generates, as the source puts it, intense heat. So managing that heat, getting it out fast, becomes mission critical.
It sounds like you need a whole thermal management system, not just a cooler.
You do. It's almost like thermal quarantine. You have to isolate that heat source and deal with it directly.
Okay, so the first, maybe slightly surprising choice was the CPU cooler. They put a 240 millimeter AIO liquid cooler, an all-in-one on that low-heat Ryzen 7 5700X.
The MSI Mag Cur Liquid E240.
Now wait, why liquid cooling for a CPU that barely sips power? A simple, cheap air cooler could handle that easily, right? Seems like spending money unnecessarily.
But see, that's the clever bit. The AIO isn't really there just to cool the CPU.
It's not.
Not primarily. It's there to help manage the overall case environment, specifically for the GPU.
How does that work?
Think about a big tower air cooler on a CPU. Even if the CPU isn't hot, that cooler is a huge chunk of metal right in the middle of the case.
Okay.
It can block airflow. Or worse, it can actually suck up hot air rising from the GPU below it, messing up the clean airflow path you want for that 5090.
I see. So the AIO gets the CPU cooling completely out of the way.
Exactly. By using liquid cooling for the low-power CPU and mounting the radiator up top, configured as an exhaust.
Pushing CPU heat straight out.
Right. You create two distinct thermal zones. CPU heat goes up and out. That leaves the entire rest of the case's fan system free to focus 100% of dealing with the massive heat coming off the 5090. No interference.
That's actually brilliant. You're isolating the heat streams. Okay, so you've cleared the path. Now, how do you actually move all that GPU heat out efficiently? That needs serious airflow, which must mean the case choice was critical too.
Absolutely critical. They used a specific case, the MSI Mag Pano M100 RPZ. It's designed with features that really help here.
Like what?
The big one is the dual chamber layout. It physically separates the main motherboard area from the power supply and all the cable mess behind it.
Keeps the cables from blocking the air.
Precisely. You need a clear, unobstructed path for air to flow directly over that GPU and then out, especially with the kind of power cables the 5090 needs.
Speaking of cables, yeah, those new power connectors are beefy. The source mentioned it was a tight fit, right? Required some special handling.
It did. That new 12V HPWR connector for the 5090 delivers a huge amount of power, but the cables themselves are pretty stiff because of the spec.
Right, hard to bend sharply.
Exactly.
Yeah.
And in a potentially tight space near the side panel, you don't want to put a lot of stress on that connector or the GPU socket. So they used an L-shaped 12V HPWR conversion connector.
Like an adapter.
Yeah, basically a little right angle adapter. It just lets a main power cable plug in and then immediately turn 90 degrees without putting any physical strain on the connection point.
Smart. Ensures a safe, secure connection, especially under constant high load. You don't want that wiggling loose.
Definitely not. It's about stability and longevity too.
Okay, so we've got the VRAM-Focused, we've got the physical setup, the platform, the cooling isolation, the airflow-friendly case, the careful cabling. Now, we get to the secret sauce, the real aha moment.
This is the part that really elevates the build, I think.
The technical trick that makes this thing a truly dedicated, quiet, efficient AI machine.
Yeah, this is where it gets really interesting, because the absolute key optimization here was achieving cooling control independent of the operating system.
OS independent cooling. Why is that so important?
Think about it. When you're running these huge LLMs, maybe for hours or even days,
Like long processing times.
every CPU cycle counts. You absolutely do not want some background software utility like the typical fan control software that comes with motherboards.
Like Armory Crate or similar stuff?
Exactly those. You don't want them constantly running polling sensors, eating up CPU resources, or potentially being slow to react when the GPU suddenly ramps up.
Okay, that makes sense. You want the OS completely focused on the AI task. So the goal then is control the case fans based on the GPU temperature, but do it directly from the BIOS, before the OS even loads.
That's the holy grail. Pure hardware-level control.
Hmm.
But there's a snag.
Oh, always a snag.
Your standard B550 motherboard BIOS, it has no idea how to read the temperature sensor directly off the third-party graphics card like an NVIDIA 5090. You can read CPU temp, motherboard temps, but not the GPU core.
So
Yeah.
how did they solve that?
They used a feature that's on many motherboards but often ignored, the T-sensor terminal. It's a little 2-pin header.
T-sensor, temperature sensor, what's that normally for?
Usually it's intended for custom water cooling loops. You'd put a temperature probe in your coolant reservoir and plug it into this header so the BIOS can monitor liquid temps.
Okay, so they repurposed that header. They basically tricked the motherboard.
Precisely. They tricked the motherboard into thinking the GPU was the thing it needed to monitor via that T-sensor header.
Clever. But how did they get the GPU's temperature signal to that header?
With a tiny, inexpensive piece of hardware, a 10K NTC thermistor.
Okay, whoa. Thermistor. Sounds complicated.
Yeah, it's super simple, actually. It's just a tiny resistor whose resistance changes predictably with temperature. NTC means negative temperature coefficient, so as it gets hotter, its resistance drops. Very common, very accurate little sensors.
And they just plugged this tiny thing into the T-sensor pins on the motherboard.
Yep, that's the electrical connection. Then comes the physical placement. They took a little sensor tip of the thermistor
Yeah.
and placed it directly onto the metal backplate of the RTX 5090.
So the backplate, not trying to get to the core itself.
Right onto the backplate. They secured it firmly with some Kapton tape that's heat-resistant tape. Now, the backplate runs a little cooler than the actual GPU core, maybe 2 or 3 degrees Celsius difference.
Okay.
But it tracks the core temperature very closely. It acts as a really good proxy. So now, the motherboard's T-sensor header is getting a live, accurate temperature reading that directly reflects how hot the GPU is working.
That is genuinely brilliant. So simple, but so effective. So the BIOS now sees a temperature on that T-sensor input.
Which it thinks is maybe water temp, but it doesn't care what it is, just that it's a temperature.
And using the BIOS's built-in fan control Q fan on ASUS boards, they could tell all the case fans, hey, base your speed on this temperature sensor input.
Exactly. Instant, hardware-level fan control based directly on GPU heat. No OS software needed. No CPU overhead. Pure efficiency.
Wow. And that allowed them to really dial in the airflow strategy too, didn't it? You mentioned positive pressure.
Yeah, once you have that direct control, you can be very deliberate. They configured it for slightly positive pressure. That means more intake fans than exhaust fans. I think it was 5 intake versus 3 exhaust in this setup.
Okay. And why positive pressure specifically? I usually hear about it for keeping dust out, which is nice, but...
Dust is a side benefit, yeah. But the main reason here is airflow control and direction. By having slightly more air pushing in than pulling out, you ensure that air is gently forced out of all the little cracks and vents in the case.
Right.
But more importantly, it creates a very predictable directed flow path. You're guaranteeing that cool, fresh air gets sucked in from the bottom intakes.
Where the GPU intakes are.
Right over the GPU.
Yeah.
And then that heated air is forced upwards, naturally, towards the top exhaust fans, including the AIO radiator, and also out the rear exhaust fan. It ensures the hottest component gets a constant supply of fresh, cool air.
Very logical. And they didn't just set the fans to blast, right? They tuned the response.
Oh yeah, crucial for making it a usable workstation, not just a server in a wind tunnel. The fan curve itself was fairly aggressive speeds, ramped up quickly as the T-sensor, GPU proxy temp rose, say starting low around 30 degrees C, maybe 25% fan speed, but hitting 100% by maybe 65 degrees C. But the timing was the key to avoiding annoying noise. They set a very fast step-up time, maybe 0 or 1 second. So when the GPU gets hit with load, the fans react instantly.
No lag.
Right. But they set a much slower step-down time, maybe 8 to 12 seconds.
Why slow it down on the way back?
To prevent that horrible pulsing sound. You know, where the load dips for just a second, the fans spin down, and the load comes back, they spin up, down, up.
Yeah.
It drives you crazy.
Yerk, yeah. Hated that.
With a slow step-down, if the load drops briefly, the fan stays spinning faster for a bit longer, smoothing out those fluctuations. It makes the machine acoustically much more stable and pleasant to be around while you're actually working.
That really ties it all together, doesn't it?
Yeah.
The whole philosophy. This isn't just about buying the most expensive graphics card. It's about strategic budget choices.
Like the AM4 platform.
Combined with really detailed, almost hidden engineering tricks for thermal management and stability, all focused on that one goal, running LLMs well. Exactly. This whole deep dive really shows that hitting peak performance for a specific niche task like local AI It demands understanding exactly where the bottlenecks are, VRAM in this case, and then optimizing the entire system around that single point. They got a quiet, stable, powerful AI machine by sacrificing general gaming prowess for hyper-focused efficiency.
And that T-sensor trick, controlling fans directly from the BIOS based on GPU temp,
Hmm.
it's elegant. It guarantees stability. It frees up system resources. Just brilliant.
Mm-hmm.
Which kind of leaves us with a final thought for you, the listener. Thinking about your own projects, your own technical challenges, whether it's building a PC, writing software, optimizing a process, where might you be relying on a clunky, resource-hungry software layer to solve a problem?
When maybe, just maybe.
A clever physical tweak or a firmware-level solution, like that little thermistor hack, could give you purer, more dedicated, more efficient performance.
Something to think about. Maybe explore on your own.
Definitely something to mull over.
Hmm.
That's it for this deep dive. We'll see you next time.